You know what? I'm going to start off with some notation. A couple students asked me questions about some of the symbols that I was using on the board on Monday. So I think I assumed that everyone knew it, but maybe some of you guys didn't. Maybe some of you guys forgot. So if I use a symbol and you don't know what it means, don't be afraid to ask. Don't hesitate to ask. And I'm just going to make a list of some symbols that you guys should know right now in case you don't. So, here's a few symbols you guys should know. What are all the ones I want to do? Okay, what's the upside down A? For all. The backwards E? There exists. How about the forward double arrow? What's this one? Implies. What if the arrow is both going forward and backwards? That is equivalent to how about, okay, so there might have been some confusion when I used this symbol, not to be confused with this one, except sometimes this one is written like this. So this one is typically, well, this one is always the Greek letter epsilon. This is sometimes used as the Greek letter epsilon, but in general means is a member of, or belongs to the set. Right? I.e., if I say x with this symbol, the real numbers, this means x is a real number. It belongs to the set of real numbers. So epsilon, however, sometimes is written much like that symbol. Okay, what about if you see that symbol backwards? Anyone know this one? It's not that common, actually. This is such that. And in fact, there's a few other symbols for such that we also use. Sometimes people just say ST. Sometimes people will use two dots, and sometimes people will use a vertical bar, for example, in set notation. So if you see the curly brackets, that means the set of whatever is inside the curly brackets. And to give you an example of the such that symbols, if you saw something like this, x such that f of x is y, this is the set of x such that f of x equals y. And it's also, you could also put the two dots here as well, x with the colon. Right, so these two mean the exact same thing. And they both stand for the word such that in this situation. Let's see, a few others that I should tell you guys so I don't forget any. Oh, okay, yeah, so we're doing limits now. You guys already were introduced to what it means if I say this. Okay, and sometimes, though, mathematicians are lazy. We're taking a lot of limits. We don't want to have to write all of this. So sometimes we might just say limit an equals L. Or sometimes, let's see, what's it also equivalent to? Sometimes we might write it like this. AN goes to L, and then we write n goes to infinity. Sometimes we might write an goes to L and then just say as n goes to infinity. Sometimes we might just say, if we're really lazy, we'll just say an goes to L. So I might have written this a couple times just because I was in a hurry. But it means, this really means the same thing as this. It's kind of bad notation, but it's okay when sort of the context is clear. It's kind of like, what else could I even mean when I write this? So when the context is clear, mathematicians will occasionally write this, when really what they mean is this. And by the way, the arrow means goes to. When we put this arrow right here. So it means an goes to L as n goes to infinity, for example. And let's see, you guys should all know that n is the real numbers. C is the complex numbers, which I could write as the set of a plus bi, such that a and b are real numbers. And z is the set of integers. And n is the set of natural numbers, which I'll say to include 0. Any others I need? Okay, I think I got them all. So yeah, if you don't know all these, it's kind of worth to have in your notes so you can refer back to if you ever see a symbol you don't know. And it will well prepare you for all the proofs that you guys are going to get to do. I'm sure everyone's really excited about it. Any questions? Okay, so let's finish up this business with sequences. There's still a couple more theorems that you guys need to know about sequences. Like the last one I told you was that if a sequence is increasing but bounded above, then it converges. So here's another convergence theorem. It's called the squeeze theorem. I always thought it'd be funny if there was a mathematician named Squee, right? And this was his theorem, right? Squeeze theorem? No? Thank you. All right. Now we've got that through with. Here's the squeeze theorem. It's what happens when you can squeeze one limit between two other ones. So let's say an is less than or equal to bn is less than or equal to cn. So we've sandwiched this limit between two others, and both of the other two, of the lower one and the upper one, they both converge to the same number. Well, it's kind of like if the thing above you is going to L and the thing below you is going to L, what has to happen to Bn? It also has to converge to L. So here's a quick little example of how you could use the squeeze theorem. Suppose we had a sequence and we knew that the absolute value was going to 0. So absolute value is like the distance of some quantity from 0. And I don't know like whether the number an is positive or negative, but I know that the distance from 0, I don't know if it's to the left or to the right, but the distance from 0 is going to 0. So what does that mean? Well, we don't know if an is positive or negative, but if it's getting super close to 0, it must be going to 0. So here's a little proof of that using the squeeze theorem. We know that an, if it's positive, it's equal to its absolute value. If it's negative, it's equal to the negative of its absolute value. Right? This always holds true. In fact, it's either equal to this or equal to this, but it's certainly not greater than the absolute value of an or less than the negative of the absolute value of an. So maybe you can kind of tell by comparing what I just wrote with the squeeze theorem that I'm going to squeeze the value of an between these two quantities. Now this one, I already told you goes to 0 as n goes to infinity. That's what was given right over here. Does this one go to 0? Well, it better if I want to be able to apply the squeeze theorem. Right? You can only apply the squeeze theorem when both of the outer two ones go to the same number. So this one better go to 0, and it will. And how do we know that this goes to 0? That's actually a limit property that we learned. Right? Okay, so like technically this goes to the negative of 0, but the negative of 0 is the same as 0. So that's by the limit property. Therefore, by the squeeze theorem, cool. All right. Pretty standard stuff. Any questions? Here's another, I guess, continuity or limit result that might be useful for you guys. It's actually kind of a restatement of continuity. If you remember the definition of continuity, I guess you must have learned that right at the beginning of 20A, I presume. So I hope you guys know the definition of continuity, right? It just means that you can draw the graph of a function without lifting up your pencil, or chalk as it were in my case. So if f is continuous, and we have some sequence converging to some limit as n goes to infinity, then, and this follows right from the definition of continuous and of the limit of a sequence, if we take the limit of f of an, that's just the same. We can, in other words, we can move the limit inside of the function. Is what we're saying. So with continuous functions, that's the crucial property, is that if they're continuous, you're allowed to move limits inside functions. So for example, let's see. We already saw that an equal to n plus 3 over n plus 1 converged to 1 as n goes to infinity. then if f of x is e to the x, the above theorem tells us that the limit of f of an, in other words, the limit of e to the n plus 3 over n plus 1 as n goes to infinity. What are we allowed to do? We're just allowed to move that limit up into the exponent up there, which, as we know, the exponent goes to 1, so this is e to the 1. Okay, so yeah, some of that stuff might help you guys on some of these homework problems. What do I have next? There's one particularly important type of sequence that is going to come up a lot, in particular as it relates to series. And that's called the geometric series. Or sorry, for now it's the geometric sequence. So let me define that. First, let's recall the example of the pizza that I was giving you. The very first sequence that I showed you guys that I was telling you is going to be kind of a motivating example for all this material. Where you started with a half, then 1/4, then 1/8, 1/16, and each term you could get from the previous term by dividing it in half. So this is an example of a geometric series. Or sorry, geometric sequence. Where, and the definition is, an, it's just some constant times r to the power n. And in that case, we call r the common ratio. So these are just going to come up time and time again. Heck, I still use them. And let's look at what happens. Let's look at the limiting behavior for a geometric sequence. Like with this one, the sequence of pizza slices, half a pizza, a quarter of a pizza, eighth of a pizza. What were these numbers going towards? These are getting to be very, very small slices. So this sequence is going towards 0. 1/2, 1/4, 1/8, so forth. In this case, an was 1 over 2 to the n, and it converged to 0 as n goes to infinity. But on the other hand, what if instead of dividing each term by 2, we were multiplying each term by 2? So how about the sequence 2, 4, 8, 16? In this case, an is 2 to the n. What's this sequence going towards? Infinity. And how do you know? So let's just take an arbitrary geometric sequence. How about with a positive common ratio? It's kind of trivial if r is 0, but whatever. So in general, how do you know whether it's going to blow up to infinity or go to 0? It kind of depends, it all depends on what the common ratio is. What's the sort of limiting case for what that common ratio can be? which determines whether it blows up or it goes to 0. Yeah, it all depends on whether it's bigger than 1 or not. So in this case, the limit of the AN, it's infinity if R is bigger than 1, and it's 0 if R is less than 1. If R equals 1, then this is the constant series, just C. Okay, so that's a geometric sequence. Yeah?
What is C in this?
This some number, some constant. In both of these examples, C was 1, so you kind of didn't see it. But in general, like, compare with, for example,
Does C always stay the same as you move through the sequence?
sorry?
Does C stay the same as you move through the sequence?
Yeah. Like here's another example. How about 3, 12, 24, 48? Wait, no. 6, sorry. 6, 12, 24, 48, yeah. In this one, AN is 3 times 2 to the n. All right, so C is 3. Be another type of example. So geometric sequences go to 0. Let's compare two sort of battling sequences and see which one wins. Because geometric sequences are about taking powers of some number. Well, let's now look at exponentials. So let's take, how about e to the x versus x to the some fixed number. How about let's just say capital N. So here x is the variable. Which one's going to win? The exponential guy wins. And okay, I'm using the word win. I didn't even tell you like what exactly the fight is. So this is what I mean. I mean that if we, let's say if we took the ratio of how about e to the x over x to the n, and n is just any integer power. It doesn't even matter. And we look at this limit as x goes to infinity. So the top is going to infinity. The bottom's also going to infinity. Here, let's say n is a natural number. So if the top's going to infinity and the bottom is going to infinity, which one wins? Well, we just said that the exponential is going to win. So this limit is infinite. And how could we show that? If this was a question, if I asked you at the beginning of 20A how to evaluate this limit, what would you do? L'Hopital, yeah. So, okay. I encourage you to verify this by repeated application of L'Hopital's rule. You'll have to apply it n times until eventually you use up all the x's on the bottom. Yeah, so I encourage you to do that if you don't remember how to. Okay, so that's what I mean by exponentials beat out powers of x. But what beats exponentials? Anyone know what function can beat an exponential? Oh, someone knows it. Someone spoiled it. I didn't think anyone would know. Okay, so yeah. Someone did say factorial, and that's the answer I was looking for. Let me remind you guys about factorials. I don't think I did this on Monday. So recall what n factorial means. It's n times n minus 1 times n minus 2 times 3 times 2 times 1 for natural numbers n. So now I want to look at the fight between an exponential and a factorial. So what about, let's say, r to the n over n factorial, where r will be some big number. Like over there, r was e. Like, yeah, so think like r equals e or some other big number. It doesn't matter. Because the factorial will always win this fight as we take the limit as n goes to infinity. This is always going to be 0, no matter what r is, in fact. So this I could prove. It's not that hard. It's a little bit tedious, the proof is. And yeah, in the interest of time, I'm not going to. But it is important to know because these types of expressions are going to be used a lot when we start doing Taylor series, which is sort of what this is all building up to. So not only, so n factorial, the reason that n factorial wins this fight is that n factorial is a really quickly increasing function. It blows up fast. Like, let's look at some values of n versus n factorial. Like 1, 2, 3, 4, 5, 6. We got 1, 2, 6, 24, 120, 720, and 7, I don't know, we're already at like 5,000 or something. I don't know. But like I want to see, like what is 100 factorial? Okay, Google. What is 100 factorial?
The answer is 9.33262 times 10 to the power of 157.
10 to the 157. Pretty big number. It's got 157 zeros. It's far bigger than the number of particles in the known universe. So this factorial function blows up really fast. You know, there's an interesting question related to factorials, which I would really love to get into, but I don't have time, so I'm just going to point it out. Mathematicians at one point were asking themselves the question of, can this function factorial be defined for non-integers? I only gave it to you for when n is a natural number. Does anyone know what the answer is? How to make sense of x factorial if x is just some number, a real number? Does someone know the answer, the function that does this? I don't know. It starts with a g. I wanted to do it in the improper integrals section. We just didn't have time. It's called the gamma function. So if you define, gamma of n, which is equal to the integral, the improper integral from 0 to infinity of t to the n minus 1 times e to the negative t dt. Also called, well, it's called what it is, the gamma function. So this is actually a continuous function that agrees with n factorial at every integer value. Like if you plotted the gamma function, it would go through all these points, 1, 1, 2, 2, 2, and then blow up. So the interesting factoid that I wanted to tell you guys is that gamma of n plus 1 is equal to n factorial when n is a natural number. So there is a way to describe factorials using a function. It's just that's the form you need to describe it. As you can see, this is an improper integral. But you can actually prove this result. It's not that hard. You just kind of have to do integration by parts, like n minus 1 times. And I really wanted to give it to you guys as like an exercise or extra credit dealy. And I found a problem in the textbook on it, but I was like, I don't have time to grade, 100 extra credit assignments. Neither does our poor TA, bless her heart. So I asked the department to get some grader help, and they gave me one. Yeah, so I'm going to see if I can come up with some problems for you guys to do that you can give to the grader and get graded, because you can't do these sorts of proofs like on WebAssign. So more info on that coming later. For now, obviously, we've got the midterm coming up. So let's, in fact, so let me just point out, this pretty much wraps up 10.1. I'm going to say a little bit more about that function in the context of series, but let me mention the midterm. So the midterm is on Friday in here, the normal class time and place. You don't need to bring any blue books or calculators as usual. It'll be just like the first midterm. I don't have much to say about it right here because pretty much everything you need to know to review it is on this outline that I emailed you guys and I put on the class website. So go over the outline. That's going to have pretty much what you need to know. I'll just give you a couple more tips, like off the top of my head is let's see. So okay, here's some hints. It might be helpful if your outline included the how to factor a to the n minus b to the n. You should definitely have all the sort of relevant trig identities. Those are liable to come up. And certainly all the complex number formulas, right? We've got a number of formulas for complex numbers like polar form and Euler's formula and sine and cosine. So no, like with regards to making your cheat sheet, the complex number business should definitely be on there. And I'm kind of surprised no one has asked me what the deal is with tables. Because we're at that point in your calculus education where you've been presented with the table of integrals. So if I were you, I would be wondering, can I just put a table of integrals on my cheat sheet? Yeah, so all right, here's the thing. Most of you guys are planning to be engineers, right? Last time I asked, 3/4 of the class said they were planning on being engineers. So once you're an engineer, I think your boss is going to be perfectly fine with you using a table of integrals. right? And since I'm supposed to be teaching you guys to do that, as well as problem solve, but also prepare you for work, so I'm fine with it too. That said, I mean, here's the context where I'm fine with it. You can put it on your cheat sheet. You do not need it on your cheat sheet, though. And if I just ask you to solve a problem and I don't say how you need to solve it, then you can use the table. And you can even say, where you're supposed to show your work, you can say, this formula was on the table, you just need to be able to write out the full formula that was on your table. Okay, so the answer is yes, you may use it, but you do not need it. And if you do use it, be able to fully justify using it and say exactly what you used. Do I need to write that down? Okay. Okay, let's see. I think, okay, now, so I'm a bit behind on schedule, so I am going to get into 10.2 right now. So let's continue looking at this guy right here. I said it goes to 0. No matter what this number r is, this quantity right here is going to go to 0. And not only that, it goes to 0 really fast. Not only that, it goes to 0 so fast that I can add up, say, r1 over 1 factorial plus r2 over 2 factorial plus r3 over 3 factorial plus dot, dot, dot. I can add up all these numbers, an infinite number of them, and I'll still get a finite number. That's how fast this sequence goes to 0. Like, not only does the last term go to 0, the sum of the terms goes to 0, which is not always true for these sort of expressions, which are called series. So that's the subject of 10.2. A series, the informal way to think of a series is, okay, we just learned sequences. When you have a sequence, you list each term of the sequence in a certain order. With series, you add each term of the sequence in a specific order. So a series is a sum of terms of a sequence. So specifically, given some sequence, let's say, an, the sum from n equals 1 to k of an, which will be a1 plus a2 plus a3 plus all the way up to a k minus 1 plus a k. Okay, so that's just you add up the first k terms of the series. And like with sequences, which I said always have an infinite number of terms, the series that we're really interested in also are infinite. Okay, so we're going to be adding up an infinite number of numbers here. So those are written the sum from n equals 1 to infinity of an. So that's just a1 plus a2 plus a3 plus ... and it never stops. So you might be asking yourself how to make sense of this. Like, how do you make sense of adding up an infinite number of numbers? And in fact, you can't always make sense of it. So we're going to see lots of examples where weird stuff happens. But the sort of natural way, and the way that we'll define it, is in terms of limits of the so-called partial sums. So this expression right here this is what I will call the kth partial sum of the series. Of the series, the sum of an. So it's, like I said, we're usually going to be looking at infinite series. But the kth partial sum will be only the sum of the first k terms. So the kth partial sum is equal to the sum from n equals 1 to k of the series. And we will denote this S sub k. So denoted, how do I say this? Finally, that allows us to define the convergence of our series. The series converges if the partial sums converge. So you might sort of be losing track of all the different sequences we had here, right? We started with a sequence a sub n. We then created a series by adding up the terms of the sequence. We then created a new sequence, which I'm using the letter S for, which are the partial sums of the series. So there's multiple sequences going on here. There's this sequence, and then there's the sequence of partial sums, the SKs, which are sums of the ANs. So we already know what it means for a sequence to converge. So this definition now makes sense. We also use the same terminology if it doesn't converge, right? We say it diverges. I'm not going to write it because we already defined if a sequence doesn't converge, it diverges. If it blows up, it diverges to infinity. But OK, so let's see an example of this in action. So let an be 1 over n, how about n plus 1? And let's examine the convergence of the series associated with this sequence. So the sum of the ANs, this is going to look like, let's see, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5, ... Any guesses as to whether this series converges? Does it look like adding up this infinite number of numbers? Will that just keep getting bigger and bigger and bigger until it goes to infinity? Or does it approach a certain specific value? Huh? The terms go to 0. These guys do, yes. So important thing to notice, it's an excellent observation, is note an goes to 0. But, and we're not going to have time to do it today, that's actually not sufficient to say that the series is finite. You can have terms where the individual terms go to 0, but the sum blows up to infinity. There's a very classic example of that, which unfortunately I don't have the tools yet to prove it to you. So we'll have to do this example later. It'll come up, but certainly the terms have to go to 0 for it to converge. So, but like I said, that's not sufficient. In this case, let's see that we shall see that in fact we can find exactly what this series converges to. So to do that, I exploit a little trick. Let's see. an, which is 1 over n plus 1, I can write as 1 over n minus 1 over n plus 1. Yeah, go ahead and check that. So, this sum, in fact, so here, let's look at the partial sum. So the kth partial sum, which is the sum from n equals 1 to k of an. So that'll be, okay, let me write it all out here. 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. And then we'll have, the last term will be 1 over k minus 1 over k plus, no, k minus 1. Oh, sorry, no. K plus, wait. 1 plus 1 over 2. So it'll be 1 over k minus 1 over k plus 1. And this will be 1 over k minus 1 minus 1 over k. So does anyone notice what cool trick I can do right here? What? Yeah, a bunch of stuff cancels out. Like here I've got a minus 1/2, it cancels with the plus 1/2. Here I've got a minus 1/3, it cancels with the plus 1/3. Minus k cancel with a plus k. So in fact, all these terms, all the interior terms cancel. And what's left is just the very first term and the very last term. So that's called a telescoping series, when you get all the interior terms canceling. Yaquin?
On the term on the bottom, the far left, how does that not cancel with the term at the last term? The term, yeah, that one for the last term. How do those not cancel?
This was a k plus 1. This was a k minus 1. Yeah. So this is a so-called telescoping series. Right? That's the term for when all the middle terms cancel. But what's so great about it is we can easily take its limit. What is the limit as k goes to infinity? Yeah, this term goes away. The limit as k goes to infinity of the partial sums is the limit as k goes to infinity of 1 minus 1 over k plus 1. This goes away when you take the limit, and you just get 1. So this was an example of an infinite series. We added up an infinite number of terms and got a finite number, specifically 1.